So let me welcome everyone and thank you for being with us. Today we have a talk by Professor David Brydges, and it's both a personal and academic pleasure and honor to have David with us today. In particular, I am glad to say that David was one of my teachers when I was doing my PhD studies in the University of Virginia. And David is a well-known specialist in mathematical physics and statistical mechanics, probability theory, and many other things. And so today David is going to speak about the Berezinskii-Kosterlitz-Thouless transition. So please, David.
Well, Carlos, thank you very much for inviting me to this beautiful place. I'm so happy to see it and to be here. And thank you all for showing up. I know that you are not specialists in the kind of thing I'm talking about, but I tried to design this talk so that it is not as bad as the title makes it look. And I'm sorry about the missing accent on Mexico. So I need one of these things here. Yeah. So yes, there is physics in this talk, but I am only going to talk about mathematics, basically, except that I will explain sometimes the physical ideas which the mathematics is implementing. Sometimes it helps you understand what motivated something. So there is this Nobel Prize in 2016, Kosterlitz-Thouless and Haldane, and I'm going to explain a little bit of what is behind that. And to do that, I have to explain a model in statistical mechanics called the Rotator Model. And then don't be frightened about the cohomology if you are an analyst and you don't feel that that's exactly your friend, because it's a very down-to-earth and concrete application. In fact, it helps me understand cohomology in a way that makes it more relevant to my life. And then there is, as you see, some transition to something called the Coulomb system. I will explain what all of these things are as best I can. So the beginning of the talk is this rotator model. Now, in physics, we are very often thinking about maps of one space to another, and we are trying to integrate over all possible maps. That's a very difficult thing to do if you're literally talking about functions from a manifold to another manifold, but it's much more concrete and immediately understandable if you make a transition to finite dimensional spaces. So here on the left, I have a finite subset, just 9 in this case, 9 elements, and I'd like you to remember this letter lambda. That will refer to the finite subset of Z2 in that picture. There are colors on these slides which we've lost, which is bad news for me as well as for you, because I put things in red to remind me to say things. So who knows what will happen now. Then we have a map from these 9 points, from the subset lambda, into the, think of it as the unit circle. So these are a unit vector that I've drawn for each one. And I call this map theta because I think of it as an angle-valued map. And theta is a map from the lambda to the interval minus pi to pi. Don't worry about the fact that minus pi and pi are both included and they represent the same angle, because we will be doing measure theory, and the measures theory will not notice that. I denote this map in a strange way. Instead of writing theta of x, I write theta subscript x. It works better for various reasons to use that unusual notation for a function. So theta is a function on lambda. Its value at a site, I use the word site, or sometimes vertex, for the points in my finite set. Its value there is at theta sub x. And we are going to, if you like, integrate over all possible such maps from a finite subset into the unit circle. Okay, now, so unit circle. Theta is, in physics, is called a spin configuration. There, this little arrow represents the direction of something with spin. And d theta is going to be the Lebesgue measure on the set of all these maps. So you see we have minus pi to pi to the power of lambda. That means all functions from lambda to the interval minus pi to pi. This is the probability space for our discussion, the space of all possible maps. And d theta is just Lebesgue measure on this space. And a model of magnetism for our talks today is just a probability measure on the space of all maps, the space of all spin configurations, the space of all maps, or minus pi to pi to the power of lambda. They all mean the same thing. Now, in statistical mechanics, we study magnetism by making simple models of it, which are supposed to capture some basic facts that we observe in nature, like permanent magnetism, for example. And the simplest models are called nearest neighbor models, and they have this structure. So this is, I'm going to start describing a probability measure now on the space of all maps. We have in the graph, so I put edges here because if we back off for a second, between there and there, these are nearest neighbors. And so we could be doing this for any graph, actually, this construction. For every pair of nearest neighbors, I imagine there's an edge in a graph. So I think of this as representing a graph. And for each edge, there is some function, which I will specify more later, of the difference of the angles. And we take the product over all the edges in the finite graph, which is this lambda. I only showed the vertices, but we can draw the edges. It would clutter it up. And then we have the Lebesgue measure here. And f has to be an even periodic function of that difference. It has to be even because otherwise I'd have to worry about whether I wrote theta x minus theta y or theta y minus theta x, and I don't want that. So we make it even, and it has to be periodic because these are angles. And then more correctly, we want a probability measure, and so we should divide by whatever the constant is that normalizes that expression. And physicists are very sloppy about, and I will be sometimes too, about this normalization. We all know it's there, and we tend to leave it out in formulas to make them a little shorter, but it's always there in any probability measure. And it is always defined to be whatever is necessary to be there to make it a probability measure. So we use the same letter Z, even though we may be, in fact, be talking about different measures sometimes, because we always know that's what it means. It's called the partition function. So in this case, since it has to normalize that measure, it must be the integral of that stuff. And that is what it is. That's the formula for it. And the partition function plays a much larger role than you would ever expect if you were in probability. Probabilists never worry about what it is that you need to divide by to make your measure a probability measure. And they don't think there's any information in it, but there is, and the physicists work a lot with this partition function, as I will. Now the Rotator model, as it's called, this is a name for a particular model of magnetism. It's this explicit choice of capital F. So to each edge, there's going to be a product over edges, and to each of those edges, it's going to be this function f of the angle difference. There's a parameter here, beta. It's always greater or equal to 0, and physically, it represents 1 over the temperature. When the temperature is really high, 1 over it is really small, and this is almost 1, and then we will be talking about the uniform distribution on the space of all maps. Inverse temperature, 1 upon temperature. Now this distribution, I want you to see what this does. So here I have written out exactly the previous formula. This formula, I've written it out again, with this choice of e to the beta cosine t. So there's the e, there's the beta, there's the cosine, and there's the t, and the product, which I had in the original formula, is this sum, because it's up in the exponent, right? If I took the sum down into the front of it, it would be a product over capital F's, would be exactly this. So you should see that this is exactly the kind of function, the measure I was talking about before. When you write it this way, you see that it has the interpretation of the dot product between two of these neighboring spins. You have a site here and a site there. We have a spin at each of them. They're unit spins. And I use A dot B is A, absolute value of A, norm of A times norm of B times cosine of theta. There's the cosine of the theta between them. So it has a good interpretation. Spin at X dot spin at Y. If we, instead of thinking of the spin as an angle valued thing, we think of it as a unit vector. That's the spin at X dot the spin at Y. So the effect of that would be to encourage all of the spins to want to point in the same direction, especially if beta is very, very large, right? And if you remember, beta is inverse temperature. That means that when you're at low temperature in the physical representation of this model, it means the spins have a strong incentive. The weight of the probability measure is such that they point in much the same direction, all of them, if they can. So, now here's a remark that I need just to make the formulas coming up look a little simpler. If you want, you can subtract 1 from each of these cosines, because that will also subtract 1, and it'll still be a probability measure, right? You're just changing the top and the bottom by the same rather large constant. By the way, you should think of lambda as an enormous set, because it represents a crystal. It represents the sites in a crystal where the number of atoms is gigantic. The fact that I had only 9 of them in my picture is just because my picture wouldn't fit on the screen. Now, in physics, like in mathematics, we start off by wanting to solve some problem, and we find it's too hard, and we replace it by another problem. So the other problem, the rotator model is a nice model of magnetism, and I will be talking more about that in a moment. But there's another model of magnetism which is a little bit easier to prove theorems about. So let's look at that now. It's called the Villain model. Villain, he's a French physicist. And the first thing to notice, I don't know why there's this little hand here. I guess it's over there, but ignore the little hand. This e to the beta cosine minus t has a graph that looks like many of these things, like this, right? You understand what I mean? It looks like, I'm going to say it now, it looks like a huge number of bell curves. And you just take one of them, and you add another a bit further on, and another a bit further on, and so on, with period 2 pi, because that's the period of cosine. And so that's what Villain suggested you do. Instead of dealing with e to the beta cosine t minus 1, just replace that function, which is the capital F I was talking about earlier, by this sum of Gaussians. Sum of translates of Gaussians. This is the translation, right? You have e, the basic function is e to the minus 1/2 beta t squared, but then to translate it, you add an integer times 2 pi, because that's the period of that thing. And then you will, I couldn't figure out a way to plot this graph, but if I plotted that graph on top of that one, and if you take beta quite large, they will look very, very much the same. So that's the Villain model. Replace the role of that function by that function. I'm writing it out again so that you can see what I mean. We take the f, we replace it by this sum of translates. Everything else is the same. And so that is the formula for the probability measure for the Villain model, is this basic formula with that choice of f. Now, what is the problem for us in mathematical physics? We want to take the limit of these probability measures as the lambda increases to all of z. It can be Z2 for this talk, two-dimensional simple cubic lattice. We want to take this limit, and we want to prove that there is a weak limit for these Gaussian measures, for these rotator measures. This weak limit should also be a probability measure, and then we want to study the properties of that. And when I say should, these are all things you have to prove, that there is a limit. Perhaps you have to do it by taking a subsequence rather than actually proving that there's a unique limit. In fact, there isn't. You have to take a subsequence as the lattice gets bigger and bigger, prove that, that there are subsequences which have limits, and then study those. That is not what this talk is about. There's a science of that called correlation inequalities, and these limits do exist, and so I'm able to continue the discussion, but we're not going to do that today. We're more interested in, you take the limit in order to study how this part of the magnet depends on this part when they're incredibly far apart. We want to know what is the correlation between where the spin is pointing over here with where the spin is pointing over there. We want to study the covariance of it. And if you're worried about the fact that the spin is a vector-valued random variable, just take one component, like the component in this direction, and compare it with exactly the same component over here. That's what I mean by the covariance of the spin at one with the spin at another. Perhaps we just pick a particular direction and look in that. But that's the idea. And we want to know, how does this behave when the points A and B, which are lattice points, are very, very far apart? That's why we had to take the infinite volume limit, because we want to discuss what happens when they become arbitrarily far apart. That, by the way, also models the fact that although crystals have finitely many atoms, the number is so huge that you get a cleaner theory if you just take the infinite volume limit. Long-range order, I'm defining some terms now. That would mean that the spin at site A is closely correlated to the spin at site B. They're trying to point in the same direction. So there is some, even though the crystal is infinitely large, the lambda is infinitely large, there's some preferred direction which everybody's pointing in. That's permanent magnetism. The alignment of all the spins is creating a magnetic field which is so large that we can measure it, and it sticks to your refrigerator. Permanent magnetism, right? Long-range order. It's called long-range order because all of the vectors are aligned and they are cooperating, and that would mean that there is no decay to 0 as A minus B becomes large. Exponential decay to 0, that would be more like when, yes?
I'm wondering, are you considering a lattice, a 2D lattice or 3D lattice?
2D lattice.
2D lattice. And the spins are 2D or 3D?
The spins are, for this talk, the spins are 2D.
Are 2D?
Yes.
So on the plane, on the same plane?
Not on, well, not, no, think of it as a different space which is a circle. It could be in this. I mean, yes, for magnetism, it could be. It's better. It's a more flexible model if you think of it as a separate space. But for the particular physical discussion of magnetism, they would be the same space.
Oh,
right?
so
Yes.
they are on the same plane. as
Yes,
the
exactly.
lattice.
Right, for magnetism. But this model applies to all sorts of different things. So part of the Nobel Prize, Haldane noticed that in quantum mechanics there's the phase factor.
Okay.
And he applied this model to that. This is why it's a very powerful description of many different things in physics. Exponential decay to zero, you might expect that at very high temperature. Remember, I said that at very high temperature you get essentially the uniform distribution. That means that the spins are totally uncorrelated, even nearest neighbors, and they're pointing in all possible directions. But exponential decay to zero might be what you get when the temperature is very large but not infinite. And then power law decay to zero is another possibility. So there are these three things. The only reason I separate those out from all the other bizarre things you could imagine is that this is experience, that these models typically give these three possible behaviors. But nothing, there are no theorems at this point that I've stated that say that that's all that's possible. Okay, here are some results for the rotator model. So for the moment, I talk about all dimensions rather than two. A simple cubic lattice in 3 or 4, any number of dimensions, but always taking the circle as the target space. For all dimensions of the lattice, exponential decay is what you get when the beta is sufficiently large. This is a theorem. It's not trivial to prove, but it was proved a long, long time ago. I haven't given an attribution because I'm not even sure who was the first person to prove it.
Sufficiently
Beta
small.
sufficiently small, yes. Oh, sorry about the little hand. Is
You
the-
said sufficiently large.
Oh, I did? Oh, thank you for straightening me out. Yes, sufficiently small. So that's very high, remembering that beta is 1 upon T, that's very high temperature, very disordered system. Exponential decay of correlations means that this part of the lattice rapidly forgets what's going on in this part of the lattice as you separate them. That, if we keep with magnetism, means there's no magnetic field. It's not a permanent magnet. Okay, in 76, in dimension 3 or more, there is a critical temperature called beta sub C with the property that if you have a beta which is smaller than this beta to C, which way around? Sorry, if beta is larger than beta C, I always get confused on this. Yes, if beta is bigger, more low temperature, physically, then this covariance will not decay, and you will have long-range order. So in other words, this is a theorem that says permanent magnetism exists in this model. It can make a transition from this state where everything is disordered to a state where it is completely ordered. And I'm very sorry, but I think, no, that's correct. Yes, I've got it exactly. That's okay. I haven't misstated the theorem. That's right. So this is 3 dimensions or more, not 2. The Nobel Prize is in 2 dimensions, more complicated. In a very beautiful, so these are nice papers, and this one especially, because one of my definitions of a nice paper is that it's only a few pages long and you can read it. And that's what this is. And in dimension 2, for all beta positive, the covariance decays at least as fast as this power law. So it's an upper bound. The covariance always decays. There are no permanent magnets in 2 dimensions. That's what it means in physics. If we lived in a 2-dimensional world, you could not stick a magnet to your refrigerator, not just because that might require 3 dimensions, but because the thing you would want to stick to it wouldn't be a magnet. It's not possible in these models to have permanent magnetism. Because this decays, at least at that fast. So a power law decay. We say power law decay, right? Because it's not exponential, separation between A and B to some power. Power law decay. No long-range order in dimension 2, or actually in 1 either. But now I want to explain what physicists did. They could not say much about this model when they first wrote it down, whether the limit existed, all those other things. But they wanted to simplify it. Physicists always try to find something that they can calculate exactly, which might have something to do with whatever the question was that was asked. Like the hydrogen atom, for example, turns out to be good enough to understand a large part of the periodic table, and it's an exactly solvable model. That was just sheer luck, right? But it happens. And here, again, we want to find a model that you can calculate exactly. Now, it's very simple when you ask a person in statistical mechanics, what kinds of things can you calculate exactly? Pretty much, at first, there are only two answers. Independent random variables, that's infinite temperature in our case, or Gaussian. So this is the Gaussian approximation to this model. So I'm going to start to use this notation for this difference between two spins, which at site X and site Y, which are nearest neighbors. It looks a little bit like a finite difference gradient, if you like numerical analysis, right? And I'm going to start calling that delta of theta. Now, I should be calling it d of theta, because this is the beginning of of our excursion into cohomology appearing here. But I can't call it d because I've got d of theta, which is my Lebesgue measure, and it would be very confusing. So I have to call it delta. Delta of theta of the edge of the graph xy is the theta at one end minus the theta at the other end. And it will matter now which is x and which is y, which one you put first and so on. But don't worry about that just for now, because these are even functions of delta theta. So we don't have to worry about the orientation of x followed by y or y followed by x at the moment. So we just replace, you see I've crossed that out because that's the minus 1. I want to be very sloppy about this minus 1, and just because I pointed out before that you can subtract 1 from anything you want as long as you do it in the top and the bottom. So I've subtracted 1 from here, that's that term, and I don't want to keep writing it because it'll clutter up the formulas. And then I've taken the quadratic Taylor expansion. Cosine of t is 1 minus a half t squared. There's the 1/2 t squared. So it's an approximation. We cannot justify this approximation at the moment. This is physics, how they do it. They just make one without knowing whether it's going to work or not. Also, we have to replace the circle by the whole real line. Oh, sorry. Minus pi to pi is replaced. This is the range of integration. In the you remember I'm integrating over values in the circle in my measure, in my basic rotator measure, but I'm just going to extend it from minus infinity to infinity. Another uncontrolled approximation. No idea whether it's good or not. Just do it. The probability distribution becomes Gaussian. That's a Gaussian means the exponential of something that is a quadratic form in theta. So it's this thing, and we still have the Lebesgue measure, but now it's the Lebesgue measure on the space of all real valued, all functions on lambda which are real valued. And here's the notation that I'm going to use. That's an inner product, d theta, inner product, d theta. I'm thinking of d theta as a function on the whole of lambda, actually on the edges of lambda. I'm thinking of it as a function on the edges of lambda, and there's a little L2 Hilbert space, which is to take this function and square it and sum it over all the edges. Sum over the edges, theta x minus theta y squared. So notation, defines the inner product. Now, one thing you can do, if you're an analyst, you should be thinking of this as something like the Dirichlet form, if you know what that is. It's a we all like, in analysis, we all like the integral of gradient of phi squared. And if you like that, then, and you want to get close to that, well, in these models, you have to write a finite difference version of it. So instead of an integral, you have a sum, and instead of a gradient phi squared, you have a discrete gradient phi squared. But then, you know, if you're an analyst, that if you want, you can integrate by parts. And you can write the integral of gradient phi squared as the integral of phi Laplacian of phi, with a minus sign in it. Well, you can do summation by parts, exactly the same operation for sums as integration by parts is for integrals. And you take one of these gradients and you move it over to the other side, so it becomes an adjoint. That's what integration by parts does. And it creates something which by definition is called the discrete Laplacian on the lattice. That's what that minus Laplacian is. It's the discrete Laplacian on a lattice. Now, I've just expressed it in a very grandiose way, but what is it? It's just a lambda by lambda matrix. You have to think of this lambda that I started with as labeling the rows, and another lambda as labeling the columns, and you just have a matrix. It's a finite matrix, which is nice. There are no analytic problems, basically, for that. So, the point is, with a Gaussian measure, we can all calculate the relationship between what is up there and the covariance of a Gaussian measure. And you just have to invert that operator. And you may experience some difficulties in inverting that operator depending on what you have done at the boundary of lambda, which I have not talked about before. Let us not worry about that right now. In good situations, you will know what the inverse means. It will be invertible. And then you can calculate exactly the answer within this approximation to how does the covariance of the spins decay as you separate the points. So that will lead to power law decays. And in fact, I think I'm going to say it next. The McBrien-Spencer paper, which if you remember was the one I told you I liked because it's short and you can read it, is exactly showing that this Gaussian approximation is an upper bound on the way the covariance decays. It decays at least as fast as this Gaussian approximation says. And they have a beautiful argument that that happens in this paper. A very short, simple argument. In other words, they do some difficult things, taking the infinite volume limit and so on. They get everything uniformly in the lambda so that they can prove this. And it's simple. Now, we come to what these guys, so KT stands for Kosterlitz and Thouless, who were two of the authors that I mentioned as the Nobel Prize winners, and that's just K for Kosterlitz. And there's a Russian who got squeezed out of the picture. You know, when a Nobel Prize is awarded, some people get bigger and some people get smaller. And Berezinskii got a bit smaller, but I like to keep him in the picture because he actually also discovered, he's a Russian who discovered this picture that Kosterlitz and Thouless have the credit for. Okay, they did more than he did. I mean, I'm not fighting with the attributions, but one should remember that he also saw this picture. So this is a physical statement I'm making, so you won't understand it unless you're you like physics. But it's good for you to know what the words are, and then I can start to explain gradually what they mean in the next slides. Vortices. You can't see them there because the picture didn't come out very well. But we have a lattice, and sometimes what you will see is something like this. Or maybe I should draw it more like this for a vortex. who knows what this one is doing? Could be doing anything, because it's not, its nearest neighbors don't give it any opinion on which way it should point. It can be any way. But that going out, that configuration where you have a thing like that going out all the way forever, that would be called a vortex. That's what I'm trying to draw there, but it didn't come out very well. There are 3 vortices here. And vortices can be oriented by the thing going like this around it, or like that. And so Berezinskii and these other people suggested that these should be thought of and have many of the attributes of a charge, like in electrostatics. You know, a charge can be plus something or minus something. And then between 2 charges in 3 dimensions, you have a force, which the inverse square law force, right? But in statistical mechanics, we're not going to talk about the force. We're going to talk about the electrostatic potential. The force is the gradient of the potential. And the electrostatic potential tells you the energy of 2 charges as a function of the distance between them. And in 3 dimensions, it is 1 upon r, 1 upon the distance between them. What is significant about 1 upon r? It's the fundamental solution for the Laplace equation. That's the way we should think. So, you know, you see what I'm getting at here is, what would you mean by a Coulomb charge on the lattice? Well, you have to take that discrete Laplacian that I just defined a moment ago, and you have to invert that, and you have to study how it is as a function of the distance. So remember, I said it was a lambda by lambda matrix. So there's a point in the lattice, which is and there's another point in the lattice, and you have to study how the matrix element represented by those 2 points behaves as a function of the distance. And that would be the Coulomb potential. So lattice Coulomb charges means that they will have an energy which is the inverse of the Laplacian, the discrete Laplacian for the lattice. And then these guys suggested that there will be a very strange phase transition in this model, which you cannot see very easily when you just think about it as spins. But if you think about the vortices in the model instead, and you think of them as charges, then you can see that there might be a phase in 2 dimensions where all of the charges are bound together in pairs. Every positive charge has a negative charge somewhere near it, so that they are kind of neutral in a very strong sense. If that happened, these guys argued you would have power law decay of the covariance. Whereas there's another phase which is well known about Coulomb's systems, where the charges are much more disorganized, and not near every charge do you find another negative charge. And then you get, it's a very strange fact which you'll find hard to believe, but in this case you get exponential decay of correlations. That's called the plasma phase. So the question that I was asking a moment ago about how the covariance decays is a way of detecting whether the Coulomb system of vortices is in a dipole phase, where they all are close to each other, plus and minus charges are well paired off, or whether it's in a plasma phase. And the distinction between them is the correlations, how they decay. And this is a new kind of phase transition which was not known in physics before, which is the discovery of these people. And that's what I want to talk about a little bit. So now let me try to explain. There is a precise theorem that vortices are charges. I find this absolutely miraculous. They're exactly charges for the Villain model. I'm going to try to explain this. And it may be that when I get to the end of this explanation, I'm also at the end of the talk, in which case I can't tell you that much more about the significance and what has been discovered in this subject. But anyway, this is what I wanted to try to explain. Now, the proof I'm giving to you here was discovered, not this proof, but some other proof was discovered a long, long time ago in the 70s, by physicists. They used Fourier transform. And when you use the Fourier transform, it's very hard to understand in the Fourier transform language some physical statement in the other language. For example, why the devil are these charges why the devil are vortices Coulomb charges? So Roland Bauerschmidt and I, he's a collaborator of mine, worked out this proof, and we don't claim that it's also unique to us. It surely can't be, but I haven't done the research to find out. But I'm going to explain a theorem that everybody in theoretical physics knows for the Verlaine model using a proof that you can read about in Roland Bauerschmidt's notes, which I can give you at the end if you don't understand it here. So here's the statement. So the theorem I put up here, vortices are charges, because this theorem is going to say that in a precise sense. First, instead of edges, I mean, we've seen that we have functions defined on points in the lattice. We have functions defined on edges in the lattice, which is this delta theta. We are now also passing to functions which are defined on the faces of the lattice. This thing here, that's an elementary face in the lattice. It's called a plaquette in physics. I want to think about variables which are integer valued or 2 pi integer valued that are naturally associated to faces. So each face will have an integer associated to it. And this I will call Q. So Q is a function which assigns to each face 2 pi times an integer. And then I will define the energy of this Q. Q, by the way, is often used in physics for charge. I again use an inner product of the charge Q, the charge configuration Q, with the inverse of the Laplacian with another charge configuration. And this will give you 2 problems, because I've only defined the Laplacian so far for functions which are defined on vertices, not functions that are defined on faces. But it's the same function. In 2 dimensions, you can regard each face as being represented by a point at the center of that face. And then if you think of that as another lattice, which is called the dual lattice, it's the same function. So it doesn't matter too much, but there's a natural way to define the Laplacian and its inverse there. I even will get more precise about this in a moment. This is the Coulomb energy of Q. And it corresponds exactly to saying that the Coulomb energy of an electrostatic field is the Dirichlet form of the electrostatic field. It's the integral of 1/2 gradient phi squared. And you can write, sorry, I said something wrong there. I mean, that's right, but I want the inverse here. So maybe you can cancel that last remark. It's started talking nonsense. Let's define this. But you can see that it is the Coulomb energy, because one thing I could do is I could take a Q which assigns the value 1 to this plaquette and 0 to all the other plaquettes. That would represent a charge at this plaquette. And then I would take another, I would ask what is the energy of this configuration? And it would be that Q with that Q. It would be called the self-energy of a charge at a plaquette. Or I could take one Q of that kind there and a different Q there, representing a charge here and a charge there, and then I would get their self-energies and the energy of interaction between them, Coulomb energy. That is what tells you it's the Coulomb energy. Here's the theorem. For the Verlaine model, exact. The partition function for the Verlaine model, the normalization, is exactly the Gaussian that I just calculated, that I just displayed for you, the spin wave Gaussian. That's this thing here. That. Well, the normalization for that. Whoops. And here is e to the minus the Coulomb energy summed over all possible ways of assigning vortices or charge configurations to these squares. But in 2 dimensions, you have to sum over Q neutral, which means that for every time the Q is +1, there must be somewhere else where it's -1, so that the sum of all of them is 0, neutral. If you don't do that, you can't invert the Laplacian. It's only on those configurations that the Laplacian has an inverse. So the sum over faces of Q is 0. And although the theorem I'm talking about is only stated for the normalizations, it's more complicated to state. It's also true that the probability measures factor in the same way too, but I don't want to go into that. All right. Now this is where some quite nice, you can, if you know about cohomology, you will see that I'm just talking in a strange language about things you know very well, better than me. So we're going to do, on manifolds, one has differential geometry. There's an operator called D, called the exterior derivative. Its square is 0. And cohomology is a subject expressed in terms of this D for differential manifolds. Now we can do exactly very similar thing for this discrete thing. And in fact, nowadays discrete geometry is very popular. Maybe for not just for this reason of this talk, but for other reasons too. It's a naturally good thing to look at. So vertices, thinking of a graph, okay, thinking of lambda as an object that has sites in it, or vertices, and then there are edges, if thinking of the nearest neighbor, lines between them, and then there are these little squares that I was talking about. Vertices are going to be that set lambda plus an additional point called star. And this additional point is attached by edges to every point on the boundary of lambda. That makes, lambda was a two-dimensional array, but if you do this, it will make it into a hollow cone. Then we have edges, which is just what I said. It's all these nearest neighbor edges, which I haven't drawn in, but in addition, you have to add all these edges, like that one, from the boundary to the star. What I'm doing here is I'm making my space compact. I'm adding a point at infinity called star so that I will be in the realm of compact spaces if we were doing analysis which wasn't discrete. Faces include the new faces like that one, which are forced on you by adding the star with this construction. Vertices, edges, faces have a property called orientation. So the edge where you travel from there to there is not the same as the edge that you travel from there to there. And one is called is said to have plus orientation, and the other is said to have negative orientation. And you just make some choice on how to do that and stick with it forever. I think I've got everything that's covered on this now. Let's look at this. What is so now we're going to talk about differential forms in the discrete setting. There are things called zero forms in differential geometry, and they are just functions on the manifold. So I will say that this theta is an example of a zero form. It assigns a value to every site in the lambda. Then we have one forms. To every edge is assigned n sub xy. This will be integer valued in this discussion, but at the moment you could think of it as real valued or complex valued or anything. It depends what kind of cohomology you're doing, what the coefficients are. But it will be integer valued for us. So to every edge in the graph, there are functions on edges, and these functions assign integers to each edge on the graph. And they do so subject to this rule. If you reverse the orientation of y and x, you reverse the sign of the function, which is exactly what a differential one form does if you know about those. You know, you evaluate it on a vector this way, you evaluate it on a vector that way, and so on. The beauty of this subject is very elementary, and you don't have to know any differential geometry. So just ignore all my remarks about differential geometry if you don't know it. It's just for the benefit of those who do. Two form. To every face, P, there are functions on faces which assign to every face integers. Three-form. The topology, remember I said that we've made it into a hollow cone by attaching this extra point at the start. So I would like to fill in the cone by a three-cell. That's a three-dimensional object, which is the interior of the cone. The reason for doing that is that now the topology of the object becomes trivial. It's contractible, right? If you imagine a solid cone, it'll be contractible. That will solve some problems which we will encounter in a moment. Exterior derivative. You have already seen the exterior derivative as an object that takes a zero form, functions defined on sites, on vertices, to functions defined on edges. To the edge xy, we assign theta x minus theta y. This is the exterior derivative in this language of theta. Very simple thing. In general, there's going to be a delta theta for these other functions defined on faces and so on. The definition is always the same. You define delta theta at an edge to be the sum of the thetas at the boundary points of the edge. One of them counted plus, one of them counted minus, according to the orientation of the edge. For a one form, we can define a two form by doing something like taking the curl in elementary calculus. You sum. So you take a function n, which is defined on edges, and you promote it to being a function defined on faces by saying the value of the new function on the face p is the sum around the boundary of the one form. It's like integrating a vector field around a cube, around a closed curve. For the two form, q, we define the three form, the exterior derivative of q, as what it assigns to a cube, or C isn't a cube. There's only, in this geometry that I'm talking about, there's only one cell. C stands for cell, which is the interior of the whole hollow cone I was talking about. We assign the sum over all the faces in the boundary. So it's easier to draw it with a tetrahedron. To the interior of the tetrahedron, we take the value to this face, the value of that face, and the value of that face of a two form and sum them up with a consistent orientation like this. The orientations are critical, but it's hard for me to go through them in detail at the moment. When you define the delta this way, it always obeys the equation delta squared is 0, like the exterior derivative in differential geometry. But it's very elementary here. We can define the Laplacian in a very general way on all of these functions. Functions on 0 forms, 1 forms, 2 forms. We can define them all at the same time by this beautiful formula here, where the star means the adjoint of delta. You remember those inner products I introduced a while ago about sum over edges of delta theta squared. There's one of those for edges, there's one of those for faces, there's one of those for the three-cell. You have an adjoint relative to that inner product, and you define the Laplacian this way simultaneously on all of these things. Now, I sloughed over the question of whether the Laplacian is invertible, but I've set things up here so that it will be. The question is it all right if I stop at 5 past, or is... Yeah. Yes, okay, because I think... All right. If you give me... This is the basic question of cohomology, in a way. If you give me an object Q that is a two form, meaning it assigns integers to faces, or any other form. Okay, we can ask this question for 3 forms, or 1 forms, or 0 forms, but let's do 2 forms. You would like to find an assignment to edges such that delta n is q. Can you solve that equation? That's the question. And if you can solve that equation, is there more than one solution to it, and how can you characterize them? Now, the solution can only possibly exist if the given q obeys delta of q is 0, because remember, delta squared is 0. All right? So what we're doing here is very much like linear algebra, but you're doing it with matrices that are not invertible. And if you want to solve ax equals b when a is not invertible, b will always have to obey some condition. And the delta squared set expresses this. Let's look at an example of how to solve this equation so you get some feeling for what this means and what it has to do with charges and so on. I'm going to find the n for a specific q, and this is the q. The purple guy means that there's an orientation, let me make it, this is, there's a, I would call, you know, when I'm repairing things with my screwdriver and I do this and I'm tightening the screw, let's call that a positive orientation, right? So there is, I'm going to put q to be +1 there and -1 there. Because that will involve this when I've got, well, you can't understand what I'm saying right now, but I'm now going to find the n that solves that. So the given mathematical problem is that to this face is assigned +1. To all the other faces, for instance, that one there and that one there, is assigned 0. And to that face is assigned -1. Last time I checked, +1 plus -1 is 0. That's neutral. We can, and that's the delta squared condition. That's the, it obeys the delta condition. So we're going to be able to solve this if we can. Now we just look for one. I put an edge, I put +1 on that edge, +1 on that edge, +1, +1, +1, and +1. I put those, that's my candidate for the solution n for delta n equals q. Will it work? And when I say that's what I put +1 on, I mean 0 on everything else. 0 there, 0 there, 0 there, 0 there, right? Now, does it actually do what it should? So is delta n this q? Let's look at that. +1. I have to integrate around the boundary to see if I get, I have to integrate, delta of n means integrate round the boundary, or sum round the boundary of the purple cube to see if you get +1. +1, 0, 0, 0. Oh, I'm so clever. 1, yes. Okay. Same thing here. That's 0 plus 0. And then it's going around the other way, right? You see, which one did, maybe I got them the wrong way around. That one's the one, no, I said it terribly badly. I got it the wrong way around because I can't understand my left and my right. Damn. Oh, where have I gone? Sorry, that was a -1, because that is going around the opposite way, I think. Okay, that's a -1. Doesn't really matter. You make a convention, but you can all agree that going around that way is going to be the opposite of going around that way, right? That's the important thing. So if we call that one +1 there, that one will be -1, right? But now there's a very difficult constraint. Delta of n has to be 0 everywhere else. And now that we may not have succeeded in doing. For instance, around here, is it 0? Well, yes, because I put zeros there, right? Around here, is it 0? That one, yes, they cancel out, right? It really works. I could do different solutions, though. I could, for example, rub those out and go up here and then come back. I could do, basically, the construction is to take a dotted line joining the centers, and for every edge that crosses it, make it plus, which way did I do it? Make it plus, make it do that for every edge, like that. You could take any other curve, and it will also give you a solution. Put all the edges that cross it to plus, and make all the others 0. A little bit like a line of electric force, actually, right? Going from one place to another. But it doesn't look at all like the pictures that you saw in your textbooks in high school, where there were lines going out in all directions, right? But we can't do that here because this is integer valued. We cannot have many different things with carrying different things, because they would have to be like a half and a half rather than 1 and 1. Integer valued, there's not so many solutions. Physicists refer to a string attached, a string joining two places. Okay, now here's a theorem. Oh, I'm so sorry, I'm going over a bit here. Exactness. For every delta q, for every q that is neutral, there is an n, which is what I was showing you there. It's a rough idea of how you might prove this. There is an n such that delta n is q. And moreover, if you have another solution, the difference between them is delta of the one before. This is cohomology coming in, exact sequences. And characterization. It's a characterization of what solves this equation. And I do not have time now to complete this argument, but I can show you a very nice formula, a very nice thing with summation that is kind of key to doing this. Give me any function f of n where n is summed over all 1 forms. I will break up the sum into 2 stages. If you compare that sum with that sum, they are summing over the same thing there, but there's a condition there that the n that you sum over, instead of summing over all n's, you only sum over those which obey this equation. Delta n is q. Now, you put this front sum in front, which sums over all the possible values of q. To make it, it's called the Pigeonhole Principle, right? You have a large class of objects, you define them into subsets, you sum over the subsets, and then after that you sum over the sets of subsets, right? It's the same principle. The crucial thing when you're doing this is to make sure you don't count anything twice and you don't not count anything. So you have to have exact, this maybe is the meaning of exact. Exact sequences, what I was just talking about before, is that theorem is what you need in order to know that you will have all of the possible values when you impose that constraint. So you can break up your sum over edges into that, and then you can use it. Instead of that writing that sum where delta n has to be q, I can use the second half of the theorem I just stated about what the different possible solutions to delta n equals q are. You find one solution, just like in ordinary differential equations, you find a particular solution, and then you add all of the solutions to the homogeneous equation to it. That's what I'm doing there. You write n as a particular solution that is one thing that solves delta n equals q, and then all the other solutions are delta m, are of the form delta of m, where m is in the vertex set. So I am transforming the original sum, which was over edge variables, to a sum over things that live in the class above, which are face variables, and things that live in the class below. And then basically, I will just show you one line where something critical happens. So we want to prove this theorem, okay, and I'll just show you a critical line in the proof. You remember that it's for the Villain model. And I just want to show you one thing here. From this line to that line there. You did something very, remember that the Gaussian approximation was replaced the circle minus pi to pi by the real line. It's a very dramatic thing to do because it's a change in the topology. In fact, when the physicists did that, they lost all the vortices. So it's a bad approximation because all of the vortices in the configurations were lost when they did that. Now the proper argument, which gives you this theorem, which restores them all, is to understand how to replace the integral over a compact set by the integral over the whole real line. The theorem I just showed you is exactly what you need to do that. I have to stop here. There's a wonderful story, but that's the proof is rather simple, but we don't have time for it. And I would just like to end with a list of people that have made nice contributions to this. If you're interested in this subject, my colleague Roland Bauschmidt taught a course in it at Harvard, which he was about one day ahead of the students in terms of, learning something and then telling them the next day. But he's a very clever man, a brilliant man, and he was able to do this, and his notes are marvelous. And you can read about a lot of this there. Thank you.
Questions? Remarks?
Well, the title was the phase transition, right?
Yes.
So the phase transition is the appearance of the vortices.
No.
On one side,
okay.
on the phase, there are no vortices, and then there appear vortices
So
when you cross the critical.
Okay, thank you for the question, because I should have explained this, and you put your finger on what I should have said. On one side of the phase transition, which is the low temperature side, there are vortices, but they're all next door to each other.
They do not.
There are vortices, but for every vortex, there's another one very close to it. So that if you look for of opposite sign, yes, so that if you look at it together, you don't see a vortex in that sense, right? Because they cancel each other. Now, the cancellation, this is a subtle phase transition. The cancellation is on all scales. Namely, so for example, what do we mean? You could say, I want to look at everything that happens at distance 2, at distance 4, 8, 16, 32. These are scales of length, right? So if you look at how often a vortex has another vortex at distance 2 which cancels it, well, that'll happen 50% of the time, right? I'm say, for the point of view of this argument. Then you go to scale 4, and you find that more of them are cancelled. And then you go to scale 8, more of them. And it's exponentially fast in the scale that they cancel each other. It's in that sense that they all cancel each other and there are no vortices on large distances. And that's on one side. And that's on the low temperature side. And on the other side, it's not happening at all on that scale. There are the spin waves, or? That's the spin wave side, yes, right. No, the spin wave side is the low temperature side, because the vortices are cancelling each other out, and you see that the physicist's approximation was to ignore the vortices, and so you can do it on the low temperature side because they're cancelling each other. And on the other side of on the high temperature side, there are lots of vortices at all distances from each other, and that will be exponential decay of correlations in that case, because the vortices disorder the spin configurations and screw up the alignment between the original spins very quickly, exponentially fast at distance. That's the disordered phase, called the plasma phase. Exponentially, yes. And this has been proved, as I say, there were these earlier theorems to prove some of these things. But that's the physical picture for this transition. Thanks for the question. I needed extra time to say all that. Yes?
How did you use the compactness of this lattice to the star?
So what people... I'm going to perhaps not answer exactly your question, but there's always the question of what boundary conditions should you have at the boundary of a finite set lambda. You should always have boundary conditions that in some way enable you to invert the Laplacian, and there are different choices. The one I chose by putting in that point like that is analogous to saying I only want to study the Dirichlet form on functions that go to 0 at infinity. So if I had, with more time, I would explain that we look only at the functions that vanish at the asterisk. So this is decay, all functions that, think of it as all compactly supported functions. And that's the good class to study the inverse of the Laplacian on for these models. Yeah.
Questions? If not, you can always ask David more questions.
For sure, yeah.
And then so we invite you to have a drink over here. And also let me announce that Steve Sons is giving us a talk. We'll take a 10 minutes break, and then